All right, welcome back, class. We're finally on to our last topic, our last unit. After this, we are going to have a unit, or I guess a unit exam based on the last 3 or 4 units, and you'll get some more information on that on Canvas. But for right now, we need to be talking all about waves. So up here, again, this is what you're expected to do. You can read through that if you'd like. We're not going to hit everything on this because of time restraints. But if you have any questions on what any of those things mean, please let me know. One thing you will learn in this topic, and we're going to talk a lot about, is what is a wave. So a wave is an energy disturbance, or that moves outwards in all directions from a source. In other words, if we look at this diagram here, right in the middle, it's like if you throw a pebble into the water. That is what we call the source. That's where the wave begins. After that, waves move out in all directions. They don't just move maybe forward or backwards or whatever else. They end up moving out in all directions. There's other parts of the wave that you need to know as well. When you look at a wave in math, and the waves that we're going to use as well, if this is your origin line there, your waves are going to have, or they're going to go up and down. That there is going to be one full wavelength. In that, we have on the way up, when it gets to the top, we call that the crest. And when it comes back down to the bottom, we call that the trough. It's the same thing when we look at a wave like this in physics. We have going up, this is our crest, and then down we have our trough. Each of these lines represents a different wavelength. So we have another crest and another trough. Another crest and another trough, and so on and so forth. This type of diagram here, we call this a wavefront diagram. This is called a wavefront diagram. Like I mentioned, the other thing that I should make note of, in this wavefront diagram, this point in the middle, we call this the source. The source is going to be moving at some frequency, and that's going to be equal to the frequency of the wave. The frequency of the wave. Alright, perfect. So if, one last thing on this wavefront diagram, if we have a crest and a trough between each of those, that is equal to one wavelength. So again, to get a proper definition down here, what a source is a source is anything that vibrates and starts a wave. A source is anything that vibrates and starts a wave. This can be stationary or in motion. Stationary or in motion. For example, you could have light moves in a wave, the stars in the sky, sound, earthquakes, musical instruments, anything that creates some type of wave. The other term that you need to learn, you need to note, is called propagation. What propagation is it's the movement of the wave outward from the source. It's the movement of the wave outward from a source. Like in our diagram, we see that it propagates out. It goes outwards from that source. So the type of waves that we're going to look at and that you're probably most familiar with are called mechanical waves. Mechanical waves are a wave that require a medium to move through. What a medium is in physics, it's that particles that oscillate and allow the wave to move. Or in other words, it's something for it to go through. Alright, the medium could be water, it could be air, it could be oil, anything that, it could be a rope, anything that it could possibly move through. So when this happens though, the medium, or what it's moving through, is not displaced by a wave. It's not displaced by a wave, or the wave. The wave is going to transmit energy from one position to another without a transfer of matter. So waves transmit energy from one position to another without a transfer of matter. To better explain what that means, let's look at a picture here. Let's draw an example. So in this example, we're going to be out in the ocean. I'm going to have my little sailboat sitting out here. And my sailboat is on the water, and there is a wave coming towards it. As that wave comes towards it, the medium that the wave is moving through is the water. The water, though, is going to crest up here, and it's actually going to come down, and on the other side, it's going to trough as it's moving the other way, behind a little bit. So as it troughs, we'll get rid of this part here to see that a little more clearly. As the crest begins to move, this water is not being displaced. It's just going to go up, and then it's going to come back down. So if the wave is moving, and I have my little sailboat sitting on the water still, this wave has come, and now it's moved, and the sailboat's on top of the wave. As the water continues to move, or the wave continues to move through the medium, which is the water, it lifts the sailboat up, but there is no movement in the matter. What's going to happen next is the water is going to keep moving along in the same direction, and my sailboat is just going to come back down. Alright, that's the simplest form of a wave and a mechanical wave that we're talking about. We don't have big crests in our waves like the way you would see somebody surfing on it or anything like that. Right now this is just a wave moving through the water. It's going to keep coming, lift the sailboat up, sailboat's going to come right back down. There is energy transmitted throughout the wave, but there is no transfer of matter. That water's staying in the same spot, and so is this sailboat. It's just going up and down. So there are two types of mechanical waves that we need to worry about: longitudinal and transverse. The first type of mechanical wave that we're going to look at is actually a little trickier, I think, than the second kind, or second type, but we're going to look at longitudinal waves. So what longitudinal waves are is it's a vibration of the medium is parallel to the direction of the wave's energy flow. It's like you push forward on a slinky. Alright, this is also how sound moves. We can do this. This is similar to sound waves. Alright, the other way that we can call, or what else we can call these types of waves, is we can call them compression waves. This might give you a little bit more direction on what these waves are actually going to look like. So if we have a compression wave below, we have a pulse is seen as the region compressed by the compression followed by the region of a more widely spread coils. So if we think about this like our slinky, and I push on the slinky, my wave energy moves as I push it. It's not going up and down, making a wave like you'd think of as a wave. It's pushing. So you get all of these little sections where the slinky's really close together to being really far apart, to really close together, far apart, and so on and so on. Where it's close together, we call that the compression. It's where the medium is most dense due to the disturbance in the medium. Where it's compressed or where it's squeezed together, that is right where you're going to initially have your wave energy. As those are squeezed together, that means it's pulling away, and you're going to have this wider part here as well. This wider part, as labeled here, this is called the refraction. It's where the medium is least dense due to the disturbance in the medium. All right. When this moves back and forth, we call this the oscillation of the medium. It's the oscillation of the medium. And if we go from one point where it's compressed to another point where it's compressed, that's going to be one wavelength. Same if we go from where it is refracted, where it's less dense, to where it's less dense on the next section. That is one wavelength. Alright, so hopefully when we get to examples that might make a little more sense. I'll try and find a video too that I can put on Canvas that may help describe that. The other type of waves is a little more common to what you might be thinking of as a wave. This is a transverse wave. So transverse waves are vibration of the medium is perpendicular to the direction of the energy. So in this one, you're going to have obvious crests and troughs. You're going to have obvious crests and troughs. Remember, a crest is when you get to the top of the wave, and as it comes back down to the bottom, we call that the trough. This is how we see waves move in water. Alright, so up above when we talked about longitudinal waves, that was more sound type of waves, ones that we don't generally see with the naked eye, but we do see transverse waves. Alright, so when we throw a pebble in the water, this is what we see. We see this up and down propagation. The other terminology that you might want to remember, and we'll cover more on the next page, but looking at this, you have your crest and your trough, and if you go from one point, so if you go from one crest to the next crest, that's going to give you one wavelength. Alright, if you go from one node to a node 2 parts away where it's both coming up, that's again one wavelength. One trough to the next trough, one wavelength. One thing that often gets students confused is they think going from one crest or from the crest to the next trough is one wavelength. That's not true. That's only half the wavelength. It's got to go the whole way back to the next crest. All right.